Yeah, I'll get it started. So thanks everyone for being here. This is the session on meeting the challenge of satellite data continuity. I'll be moderating. I'm Travis Toth from NASA Langley. And our first speaker is Amber Soja from NASA Langley, and she's a HAQAST PI.
And you want me here? Hi everybody. So I decided to start with a little bit of whimsy and put this little, if you don't recognize it, it's smiley face. And it should be a lot of people that we've worked with over the recent years. And if I've forgotten somebody, I'm sorry. We'll get you up there for a next time, although the smile is pretty full. So it was in the spirit of what HAQAST is and the way that we bring each other together. And I know that working with everybody that's on this list, I've learned, and I learned how to look at satellite differently and how to think about what I can do for you. I've learned about your gaps. I learned about, and then it makes me think, okay, we have something that we can do for this. And it might be, it might be Jeff, it could be anybody. It's not necessarily me, but it's making connections with other people. And taking this mass of people and making it worth more than the sum of individuals even. So making it more than it could be. So that's why I decided to add that whimsy. So that this session was talking about satellite data continuity, not satellite continuity, but data continuity. And so I'm going to start by giving you some examples of what that means to me. And I have a fire, smoke, air quality perspective. So that's my perspective. And those are the examples I'll give. And then, but think about what you're doing. So it might not be fire, but it's still applicable. So on the left, we see the Williams Flats fire from Modus and Terra perspective. And I'm just third. On the right, we see Veer, Sumi, and PP. And this was, this was for 2019 fire. So Modus, Terra, and Aqua, neither instrument, caught this fire on the 3rd. So I'm going to guess, and I'm guessing it was the time of the overpass because that's a lot of detections. And Modus is they're good instruments. So I'm going to guess it's the time of the overpasses. So if you're thinking in terms of looking at long-term data continuity and you're looking at the number of fire detections, or if you're looking at a fire detection that's equivalent to an area that's equivalent to a mission, and you're saying they're increasing over time, you just have to be mindful that you're using the same data and not duplicating satellites or the resolution of the instrument. So that's one thing to be mindful of. So this is a picture, same fire, Williams Flats fire, different day. This is August 8th. This is Modus, Terra, and Aqua, both of them. So if you're a firefighter and you're planning your day, you get up and you look at this. You've been looking at these data for well over a decade. You know what you're doing. You need to plan where people are. You need to figure out if you need to get a city out of the way, to warn a city so that people can evacuate. If you're planning for resources, you might have to plan for how many choppers you have, how many people, how many aircraft. So what you're planning your day, and you look at these data day after day after day, year after year after year. And then all of a sudden, it looks like this. And we did this to people. So the firefighter, the whole community that needs this for planning or firefighter and going, oh my gosh, what the heck happened? So that was a perspective that if you're not them, you didn't have. And they don't realize that we just launched a new instrument and we're giving you all this great higher resolution data. So it just was quite shocking. So something to think about and a way to present data to the data users. So that's one reason we need data continuity, or two actually, thinking in terms of long-term data sets, whether they're emissions for air quality or fires, and also in the way it appears to people. We can frighten people. Another data continuity situation is the time that the satellites are launched. So not only the number of satellites and the resolution, but what time are they overhead? For fires, farmers like to burn in the morning when it's kind of moist on the ground. Everybody wants to control fires. The objective is always to control. So they want to burn when it's moist and the fire weather is light, Relative humidity is high, it's cooler. So the mornings are either sometimes in the late afternoon. So the fires are controllable and they want to start their day. If there's a football game, they're not going to burn because they have other things that they want to do. So our satellites are not overhead. So we miss the morning overpasses. Depending on the resolution of the instruments, we miss smoldering in the evenings as well. We miss the afternoons, the late afternoons when the fires peak. Wildfires, when wildfires peak. So thinking about the time that a satellite is overhead, no matter how many instruments you have, is also critical to thinking about your long-term data continuity. And so here you can see the different satellites. Blue is aqua, Terra yellow, Sumi orange, and NOAA 20 is in gray. All right, so we have a Tiger team that's looking at this continuity. And even though I gave the perspective of fire, there's also patterns of change that actually Travis will be looking at with other people. And the vertical distribution of dust and smoke. So that's something that we can think about over time, the vertical distribution. So if you're interested in that, I've heard a lot about the layer heights, then you're interested in possibly looking at these data. Consistency and harmonization of formaldehyde, aerosol products, NO2, gridded smoke PM. So these are also concerns. Misclassification of heat sources, inconsistency and discrepancy, and aerosol layer heights. So that's what the team is going to bring. If you're interested in joining, we would love to have you if you think there's something for you. So in previous work, we've looked at these small fires. And the way that we look at small fires is that we look at pre, active, and post. We may not get an active, we may not get satellite data in time, but these are high resolution data, and we compare it to the data that the community uses to validate the information that is used. We use any resource we have, whether it's a state resource or a federal resource. So anything we have to verify that what we think is happening on the ground is actually happening. So this is challenging. Each of these, the top line and the bottom line, are a particular landscape. On the left-hand side is over time. So left-hand side is August 31st. The second panel is the first. The third panel is the the third, and the fourth panel is the fourth. So you can see, looking at these patterns, that the burns on the second panel, which is the first, they happen very quickly and they're gone in a matter of days. So it's really challenging to get these fires, to capture these fires. And so our validation is pretty intense. This is largely for the EPA. So when we've put this data together, we find that all the satellite detections, all the satellites combined, only see about 50% of the fires in this region. And these are large, small fires. So Kansas does an excellent job of communicating the amount of area burned. So they're way up there with their relationships to the EPA. And the MODIS burned area product defines 65% of this area. So another thing we did with students is we looked at burning in Iowa. The state of Iowa was saying that they only, that the EPA was overestimating. So we went in and we looked, and we were surprised to see that they burned ditches just like they said they did, and not whole fields, and the EPA was overestimating. So what the EPA did is change their algorithm. So everybody is an honest partner, they just need the information. So that was an action from the last time that we had these type of analysis. We have a second project that is looking at prescribed fire and wildfire. So you can see this team of scientists. And the reason this is important is we know that fire is increasing on the landscape, and that's what we want. We know that prescribed fire is increasing, and the community consensus from the locals to the feds to the state to air quality organizations, when they were put together in that room, they agreed that we need to increase fire on the landscape. And that is in order to to prevent fires that will happen that are bigger and more dangerous, and for ecological reasons, for many reasons, we need to burn them these days. But just because there can be good fire doesn't mean there's good smoke. So we want to tease these apart. We want to look at the differences between large wildfires that are extreme and happen every once in a while, or the type of fires that are prescribed that are on a landscape for 3 months every year. So what are the health issues between these? We can't ask those questions because we don't have a good data set. So this team is looking at ways that we can put together a data set and validate it to be able to even address these questions. So that's part of that Tiger team. And I think I have about 30 more seconds. Do I? All right, so this is my last slide. And the top left, this is from a team, and I see a couple people that were on the team. On the top left, we were looking at Kansas, and it said that the aerosols were just really high. AOD was high, highest in years, and it was an extreme fire year. And then that didn't coincide with what we were hearing from our partners. So we looked at Calypso, found out it was dust overhead in the top right. And the bottom left, we also saw smoke coming from New Mexico. There were big fires there. Jeff Pierce talked about this a little bit yesterday. And on the right-hand side, we used the Calypso LiDAR data and looked at what the averages are. And in fact, it was a normal fire year. It was dust that was primarily covering it, and the smoke was overhead. And that's all I have. So if you want to join our teams, please give us an email.
Thank you, Amber. So our next speaker is Kazuyuki Miyazaki from NASA JPL.
Yeah,
Miyazaki, sorry.
So I'm Kazu Miyazaki from NASA JPL, and I'm not in the Tiger team. But I have been working on modeling and satellite data development and application using the data simulation techniques for both the corners USA and for the global scale. So and this picture shows the last January 2024 January fire in California. So here is the JPL campus where I work every day. And here is the brown or purple color shows the sound area.
Yes.
And that's called the Altadena city, the JPL. And more than 200 JPL people lost their house. Then 200. And as many of you might know, including myself, I lost my house there. My house is around here, in the middle. There's no way to escape. But then I'm here, I'm doing well. And okay, so our question is, how can we best use our NASA satellite data to support both, scientific understanding and the local communities recovery effort? So this is the older version. This far. Yeah. And okay. So the satellite measurement have been used to characterize the chemical signature of the wildfire plumes. So those are examples for the Eaton fire in the California south. Then first we used the troponin, NO2 and CO to characterize the enhancement ratio of those two species. Then we found that NO2 and CO enhancement ratio are significantly higher than the previous wildfires. So which indicate the greater NOx emission from the band structure and also the more powerful the fires. Also, this indicates the interaction with the existing air equation. This might be the unique situation. This is a boundary between the vegetation mountain area and the city. So those are connected very closely. The next we use the CRIS measurement on the north, the JPSS satellite. Then we saw, along the plume, we observe the enhancement of CO, ammonia, and TAN. So which indicates the chemical production of the secondary fluid and the ozone and the aerosol. And our question is, there's still remaining challenges, like satellite does not measure directly the surface air pollutant. So there's some limitation in the sensitivity and the limitation of the uncertainty of those retrieval. especially over the fire plume, it's much harder than usual situation. We also need to know the smoke plume height and how the retrieved current tell us about the surface quantity. That's always the big question. So this is my AI made the summary figure showing the key challenges in using NASA satellite observations. To inform the stakeholder or the local community aiming for the recovery decisions. So the left pole in the bottom shows some technical challenges like the conversion from current to surface and the attribution and how we distinguish the wildfire plumes from other pollutions and how we inform the local community in a timely manner. Also, how we best combine all the available information, not only satellite, but also the ground-based measurement and model. So those have been, addressed, or we are still working from our usual scientific activity. I believe that includes the HAQAST Tiger Team project. And the right one is, recovery to the resilience. This is much longer time scale. And as a scientist, we can help the longer term discussion. But then there's some challenges, like what information should be communicated with the public. If we show those things, it doesn't help anything for them. But there could be some information that might be useful to decide if they can come back to the community or they need to get away for some reason. So as a local residents impacted by the fire, myself, and as a scientist working at NASA, I'm thinking of the best way, how best we use the satellite to inform the local decision of community recovery. So the related topic is NASA's air quality photo under the Air for US project. So we are putting the effort to provide all the trusted data on air quality at one place to support the stakeholder policy decisions. And we are still looking for the community's input on what information should be delivered and how they should be visualized or presented. So your feedback will be very important for us to make it more meaningful. And about this continuity of the satellite measurement, I really enjoyed the previous presentation, but I'm here more focused on the trace gas side. So the observing system is evolving over time. And for the air pollutant trace gases, Tropomi launched in 2018 and Tempo launched in 2023 provides the much improved information at the final resolution. As a meantime, over the decadal scale, we have Aura, Terra, and Aqua. Since those are expected to reach the end of their mission in the next few years. So when we analyze the long-term trajectory of air pollutant and its emission, it's super important to consider their changing observing system. So the key is, as emphasized in the previous presentation, is the difference in the spatial and temporal scale of those measurements. So this figure shows that X is the spatial resolution of the satellite measurement, and the Y-axis is the temporal resolution. So as those geostationary satellites provide the hourly scale information at the few kilometer spatial scale. Then at the same time, LEO provides the global coverage every day or every few days. Then we have been developing some technical capabilities like AI for data assimilation systems to meaningfully combine those different satellite information with the numerical model and chemical transport model. Then in my case, I have been using the assimilation technique to make best use of available data from data sensors, and also to provide a chemically and dynamically consistent integrated data set. This is just an example. I'm not representing my own research so much today, but as an example, that my system integrates those different type of satellite measurement to constrain the entire atmospheric chemistry system, including the emission sources of the key pollutant, and its impact on the secondary pollutant formation. And we utilize those satellite-informed emission or concentration data to support the policy decisions. So we work closely with stakeholders. Then the first step is to develop the emission scenario, considering the key environmental policies, talking with the local and the federal stakeholder. And our focus is like transportation, agriculture, and ports, and we also analyze all the sectoral contribution. And applying those emission scenarios to our modeling framework. So we use GCHP, Geoscan High Performance System, which is a global model, but which has a stretched grid capability with a spatial resolution of 12 kilometers over the corners, which has been developed by Jin Hyokyu. He's my postdoc, so he's working really hard. Then we analyze the impact of those emission scenarios on the measuring pollutant under the different conditions like the wildfire and the coastal meteorological condition. Then we aim to inform the stakeholder to evaluate environmental policies and quantify or identify the key trade-offs between the key pollutant. We also try to prioritize the high impact sectors and regions. So I have just one example today, so which shows the impact of the emission reduction from each sector separately on the surface ozone over the corners. Then you see here the reduction in the on-road mobile provides the largest reduction in surface ozone, especially in the eastern United States, followed by the stationary energy emissions. Then at the same time, so those the road transportation actually increase ozone over the polluted region, including the Los Angeles area, which might be the reason for the recent increase in the surface ozone concentration. And for the central United States, the area-wide emission reduction have substantial impact. So we are putting those the information together, and those will be the input to the NASA's air quality portal website. And hopefully those will be useful to support the stakeholders' policy decisions. But any feedback or any request from the stakeholder that key, then we can optimize our approach. What should be communicated or what should be provided from NASA to support your feelings. Yeah, that's it. Thank you.
Thank you, Kaz. Our next speaker is Dan Goldberg from George Washington University.
Okay, cool. Thank you. Today I'm going to switch gears a little bit, talk about our trace gases, particularly NO2. NO2 has direct health effects. It is attributable to childhood asthma. About 5% of global childhood asthma is attributed to NO2. This is a recent study that we were co-authors on. That was also with the Global Burden of Disease. They release a study every year. So that's a quite large number, 233,000 years lived with a disability. These numbers actually a little bit lower than other prior years, but there's a large uncertainty with these numbers. In any case, NO2 directly causes human health problems, in addition to NO2 forming other chemicals such as ozone and PM2.5, which are also toxic in their own right. But then it's also harmful because it is co-emitted with other primary pollutants directly, such as diesel, PM, and CO2, VOC air toxics, etc. And also our work has shown in the past that it's inequitably distributed across the urban landscape more so than most other pollutants. So this is just a very broad overview of two instruments measuring NO2. Actually calculated there's 14 different active measurements. I put 13 there, I forgot GOSAT GW. So there's 14 instruments by my count that are measuring NO2, quite a large number. But I'm just going to talk about TROPOMI and TEMPO today. TROPOMI has a longer time record, goes back to 2018, and has about 3 by 5 kilometer pixel resolution, only measures once per day because it's in LEO orbit, sometimes twice, depending on the day. It is global. That's the big difference from tempo. It also measures some gases in the infrared, particularly methane and CO. And it's an ESA instrument, not NASA. Tempo, on the other hand, has better spatial resolution. It measures up to 12 times per day. It is data only back to about August of 2023, but it is only centered on North America. What big advantage of tempo is we have our boundary layer ozone product, which is just being released. Both of these measure NO2, both measure formaldehyde, both measure in the early afternoon, and both measure only in those cloud-free conditions. All right, so I'm going to talk about tropomi first, and then switch to tempo. So this is building off of work that we did for the last generation of HAQAST. This was looking at long-term trends in NO2 from 2019, the beginning of the tropomi record, and today, well, we've updated this to 2025 internally, but the paper is only 2024. We can see large reductions in China. They were starting with a pretty high baseline. We also see reductions in Europe, definite increases in the tropics and mixed, but mostly down in most US cities in the United States. The dark blue, you can see the dark blue spots in the major cities. Anyways, we did this for 11,000 cities. We showed in the paper which are statistically significant, which are not statistically significant. The city with the largest reduction over this time frame was Seoul, Korea. And the city with the largest increase was Moscow, Russia during this time frame. Anyways, there are a lot of interesting stats in the paper. I'm not going to go into it. I also encourage you to check out that link to the website. It has this other graphic there. But one other thing that we did in the paper was looking at emerging hotspots, particularly oil and gas and mining regions. I don't have time to talk about all of these 9 panels, so I'll just focus on the US ones. If you're interested globally, check those places out. But here in the US, we've seen some very notable rises in the Permian Basin, which is West Texas, and the Uinta Basin, which is in Utah. NO2 going up at about 6 to 8% per year, and 2026, I've looked at more recently, is quite large as well, at least in the Permian Basin, going up and up. And then obviously you can see some other global regions which you can check out at a later time. One other paper that just came out was looking at using tropomi to look at EV adoption in California. There's actually a lot of circulation in the EV space here, showing that the satellite data can actually see improvements in air quality. The zip codes that had more EV registrations had greater NO2 reductions over time. So just highlighting this paper, if you're interested in more, check it out. Last but not least, with tropomi is using it to investigate congestion pricing in New York City. What I like about tropomi compared to tempo is, again, it's long record. So we're able to calculate what I perceive to be a very nice baseline, which we only isolated stagnant wind days and over a longer time frame. So we hopefully canceled out some of the meteorological effects in the baseline, and then we compared to 2025. We can see that there was some background change in NO2, so blue everywhere. So that's not attributed to the congestion pricing. That was attributed to some either meteorology or some long-term change in NO2. That wasn't the purpose of the paper. The purpose of the paper is to investigate lower Manhattan area. And we did see somewhat of a improvement there. It's about a little bit darker, 2 to 5% cleaner in those areas. I wouldn't say that's statistically significant, but it is in the correct direction. So if you look at the New York City website, they say they don't see anything statistically significant. I would generally agree with that assumption. However, there was another paper that said there was a large reduction, and I think the large reduction was misattributing the background concentrations to the congestion pricing. So that's more my personal opinion. Anyways, continuing on. We've done some work using tropomi to estimate surface NO2. So if you're interested in that, check out this paper and this link. We have monthly data averaged for surface NO2 and then also annual patterns. There, again, just showing you a snapshot of what we can see. There's the Washington, D.C. area over multiple different years. Generally matches the patterns of what we would expect in the region. So I was very happy with this product. I encourage you to check it out and generate your own maps by checking out the reference and the data itself. All right, so now transitioning to the tempo data, we have version 3 data that's for 2 full years, and then now version 4 data that's coming out sporadically now. Hopefully we'll have a full version in a little bit. But here I'm just comparing version 3 tempo to Trobomi over a 2-year period. And we can see that the spatial patterns match really, really well from your first glance. So that's really great. However, if you do a closer look, there are some biases between the two instruments. Typically in the rural areas, tempo is showing lower values, and in the urban areas, typically tempo is showing larger values. But we can see that correlation is extremely strong, 0.89. So really great agreement. However, based on preliminary work, Jen Kaiser showed it yesterday. I don't have time to talk about it today. But version 4 is looking even better with some of these biases that are reduced between the instruments. So I'm really excited, and hopefully I will be able to show that at the tempo meeting in about a month. Okay. There is larger NO2 in the morning time. This is documented in the ground data, but we also now are able to look at this spatially across both CONUS, the continental United States, as well as individual urban areas. We showed here about 90% of the tracks experience higher NO2 in the morning. So missing that morning measurement with Trobomi is quite critical for trying to accurately characterize NO2 around the US. So really exciting that we have tempo data, and it varies by season to season. So in the summertime, we don't see quite as large a difference by hour of day. In the wintertime, we see a very large difference. And we've shown that satellite data does correlate really good in the morning time. It's a little not as good in the afternoon, and especially late afternoon. So this is just a caveat to that, especially that late afternoon time frame. It's maybe not very correlated with the surface concentrations. But version 4 is looking a little bit better. So we'll see what happens there. Okay, just moving on. Last science slide here is to show that we've been investigating NO2 disparities. So now that we have those morning measurements, we show that there's even larger disparities in most of the cities between the least non-Hispanic whites and the most non-Hispanic whites. So Lulu Chen has a paper under review. Hopefully it'll be out in the next few months that goes through this. But then also here she presented a poster on warehouses. I don't have time to talk about that. Check out her poster, which is online. Okay, so conclusions here. Both satellite NO2 measurements offer complementary advantages despite not measuring nose level concentrations. We've generated these nose level concentrations, but the satellite data doesn't itself do this. NO2 has a longer time record and is better characterization. Tempo is better potentially for these urban scale studies, and certainly at these early morning time frames and late afternoon time frames. Last but not least, we have NASA SARP coming up in 3 weeks, 2.5 weeks now. We're going to be flying out of Houston, Texas. I'm going to be there helping as a faculty mentor. If you have any interest in letting us know where we should maybe fly, we're still doing the last bits of flight planning, but most of the flights are going to be directly over Houston. And we're going to also have a few flights potentially to the Permian Basin. So if you have any input, please let me know. Again, thank you for your attention. Happy to take questions.
And our final speaker is Bob Carp from right here at UW-Madison.
Thank you, Travis. So my talk is going to be about a software package that's called HAQAST V and how it can be used to work with different types of satellite data that's related to satellite data continuity. So first off, what is HAQAST V? It's a freely available software package made at the University of Wisconsin. It's a point-and-click user interface that works with all different types of meteorological data. That includes forecast model data, point observation, soundings, radar data, and most importantly for this group would be satellite data. The University of Wisconsin is known as the birthplace of satellite meteorology, so we have a pretty intensive satellite focus in a lot of the work that we do, including HAQAST V. So we have support for all the traditional GOES satellites, GOES East and GOES West. We have MSG as of right now. We're working on the MCG FCI imager. We have support for Himawari. Along with that, other geostationary, so we have support for our GEMS, which is the geostationary over Eastern Asia, and we have support for TEMPO as well. Along with the other LEO satellites, so we have the JPSS series, VIIRS, the Imager, CRIS, and ATMS, which are the sounders. We also have support for Triponi, but we go back to older legacy sensors as well. And one thing that HAQAST is very good at is if you just have a random netcdf gridded file lying around, you can load it in and display some of your data within just a few clicks. You don't need to write up a script to load in the data, although you could. We have support for Jython scripting. You can just easily work with your data. So this is what HAQAST looks like. It's two different windows. On the left, you have your Data Explorer window. That's where you choose what data you want to work with and how you want to display it. On the right is the main display window. That's where the majority of your displays will end up. So what problems can HAQAST solve with data continuity? One approach I took to that was being able to work with the geostationary and low Earth orbit at the same time. This is a case here from 2023, where there were Canadian wildfires that were sending smoke down into the northeastern part of the United States. At the surface, we have a GOES East True Color RGB, where if you can pick it up on the screen good enough, it shows smoke over the northern Great Lakes. That is overlaid with a backpass of Calypso LiDAR data. And what that's giving you is more context about the height and the concentration of the aerosols from the smoke. So being able to look at the level 1B, which would be the true color image, along with the level 2, they both are the polar data. They add context to each other, so you kind of get the full picture. And notice the display is rotated as well. The display window is fully interactive because the software runs on Java and Java 3D. So just by right-clicking and drag, you can rotate your display and inspect it however you want. Data on a global scale, so global continuity. I just have the footprint of the geostationary satellites I mentioned at the top. On the bottom, we have the footprints of TEMPO and GEMS. And then I displayed a full day's worth of Triponi data. I just set it to a solid color of blue, just so you can see that we have full global coverage with the LEO from pole to pole. Continuity across generations. So here we're going back to 1979 in the upper left panel, looking at GOES 3 data. And it's a 16-panel chart that goes all the way through today with GOES 18, GOES 19. So you have all this data that goes back multiple generations from different satellites and instruments, but you can easily plot them in the same projection. It makes it easy to compare different things and get the full picture. And again, with going back to older data, we have support for different generations of LEO sensors as well. So we have support from MODIS onto VIIRS, and then from OMI onto Triponi. Expanding the geoconstellation. So this is a look at GEMS data. I have the URL at the bottom that I downloaded the files from. This is a total vertical column of nitrogen dioxide. So I downloaded the files. I was able to load them in and create this animation. Everything about the display is customizable, from the map lines, the enhancements, the labeling, everything like that. And with HAQAST, you don't just look at the picture, you have the data readily available to you as well in the main display window. So if you load your data and you want to inspect it, there are a few different ways that you can do it. So I have a GEMS image loaded right here. This is just one time of nitrogen dioxide. In the southeastern corner of China, I have my cursor located, my mouse. And if you hold down the middle mouse button, you can interactively probe the data values and see pixel by pixel what you're looking at. So like right there, that's 0.623 Dobson units of nitrogen dioxide. And then through Eastern China, where we have the higher concentrations of nitrogen dioxide, there's a black line going through the display. That's what we call a data transect display. So you can position the endpoints of that line wherever you want. And then on the right, you can see the concentration of nitrogen dioxide along the path of that line. Working with level 1B and level 2 at the same time. So these are the Flint Hill fires. I think I have the FIMIX labeled at the bottom. But we're looking at GOES East data. So on the left, we have the visible band 1 data, which is in grayscale. And I overlaid that with the 3.9 micron thermal infrared data, so we can pick out the fires and the hotspots and all that. Everything less than a certain threshold that I specified as transparent, so you can visualize the visible and the infrared at the same time. And then to get more of a picture of the data, you can also look at the different level 2 products. Like right there, I have aerosol optical depth, which will give you a little bit more information about the concentration of the smoke from the fires. Some RGBs, this is the next several slides are going to follow along with these Flint Hill fires. On the left, we have VIIRS, the really corrected true color RGB. So you can see some of the smoke there. I have that overlaid with METAR data as well. It's easy to time match. You get multiple what we call layers on top of each other. So if I wanted to, I could have plotted radar data on top of this. I could have added in several other things on top of this display. Then on the right, we have the fire temperature EDR, the fire temperature RGB. That'll tell you more information about where the fires are located and how hot they are. We have different types of RGBs for all the geostationary satellites that we have support for. So as long as your data source that you load in has the necessary bands and calibrations, you can create a whole host of different RGBs and channel combinations from different sensors. From OMI to TRPOMI. So here we're looking at the same variable, the total column nitrogen dioxide. I have them up side by side here, so we have the same projection, the same enhancement range. We're looking at side by side, so you can see how the resolution has compared through time. And you can also see, just compare the two sensors together. And I could plot these on top of each other as well, and you can toggle visibilities on and off. So you can make the display almost like flash back and forth as well if you want to. Gonna get through this without talking about tempo. So same case again. On the right, we have the TRPOMI data of nitrogen dioxide. Then on the left, we have tempo. So the tempo starts at the beginning of the day, plays through hourly, and then I stopped it at the observation of the TRPOMI data. Just a quick summary. So again, Makaitis V, it's a freely available software package. Anyone can download it, runs on Windows, Mac, and Linux. It's a point and click user interface, so you can point and click your way through loading the data. We have a whole variety of data that's freely available online for more real-time stuff with point observation, satellite, radar, and you can load in your own data files as well. So I download data from NOAA class or NASA Earth data. A lot of that data just loads in as long as it's compliant files. And Makaitis V can be used in a wide variety of ways with data continuity. We can go back and look over 50 years in the past and look at satellite data alongside today's if you wanted to. We have support for data on a global scale with all the different geostationary and low Earth orbiting satellites. And then we have support for the different level 1 and level 2 products. It's just my last thank you slide here. So that QR code right there, that'll take you to the main Makaitis V webpage. You'll find information about how to download, the user's guide, tutorials, and places for support. And I have my my email up there as well. So if anyone looks more into Makaitis V and has any questions at all, can reach out to me that way. All right, thank you.
So I think all the speakers come up. So we'll start with the radio.
Yeah.
Pat, you want to pick up?
Yeah, I have a question for Amber or for anyone else. Are there continuity issues for AOD years?
Yes, I would not be the expert.
Sorry,
but
can you repeat the question?
the question is about continuity issues with AOD. I would say yes, but I'm not the best person to answer that question. So I would go to someone else. Yeah. Yes, there is. Actually, AOD is a gridded product, and I think AOD in general are on the continuity tiger team. People are going to look into that. Yeah, anything with a resolution change is going to have, and time of day. Anybody else want to add to that? Got NO2, ozone here.
Maybe I can say a few things. VS have some extra wavelengths, and if their AOD uncertainty have been very much improved in VS. And when we do the surface aerosol emission estimation using MODIS and VS for the same time, there's a significant difference between those two estimates. Then the VS-based one provides much detailed constraint on the surface aerosol, but that's for just the total. We do not have the chemical specification yet, but we see some innovation with VS. I mean, when we combine those two measurements to make the longer term the aerosol analysis, it's clear we need to consider their technical impacts. But yeah, we have the paper on the evaluation of the how much improvement we can expect from beers. The paper is now in the review, but I can share some of the number if you like. Yeah.
For our stakeholders, it might be what we've done in the past is we do like 1-2 pages just with pictures and saying the differences in the, so maybe something like that could be put together.
Okay,
So it's real simple for people who don't want to read through a lot of papers, but say, these are the differences. This is what'll happen.
Okay, so send
pictures
that to you, and maybe you can share.
Yeah, I don't know if Jenny's in the room, but she posts those. Yeah.
I have 3.
Ooh.
My math teacher in high school, I've only learned one. First one, I guess I'll start, Stan. Question, your thoughts on Sentinel-5 being in a morning orbit?
Yeah, I mean, I don't know if that data has been released yet or not. Okay, but yeah, I'm really excited about different times of day globally. Based on what I've seen, when I've looked average tempo data between like 12 and 1 p.m. and 1 to 2 p.m. on average, they look very similar. So certainly certain use cases having every hour of the day can be really helpful, but I think in particular having 2 or 3 measurements per day could be really, really helpful globally. So having another measurement in the morning globally could be really, really helpful. Could hopefully get some of the rush hour traffic in the morning, and then also at high spatial resolution. So it's also great. So yeah, I'm personally a proponent of having like 2 or 3 measurements globally as opposed to trying to get geostationary everywhere. But that's sort of my personal opinion.
So can I say?
Yes.
We had before the GOM2 and schema together.
Yeah.
So the GOM2 is measuring 10:30 a.m. in the morning. The schema is close to 1 p.m. And with those 2 different polar orbit satellite, we are able to detect the morning to the early afternoon difference already. So that was really before the geostationary era. We are already able to make some diagonal engines discussion. Yeah.
That's a really good point. Thank you. And I guess I'll follow up then with my comment with Kazuy's presentation, which I wanted just to reiterate the Air for Us activity, the interagency activity between, maybe I should come closer.
Yeah, you should come to the speaker because this is an important one. The speaker is only there.
I think we can just also have the panelists repeat the questions.
This is something different. She's a program manager.
Okay.
Come over here and say that so people can hear them. This is a state.
Program manager who forgets to
Yeah.
register, so I've just snuck into your meeting. Yeah, so you've kind of heard a couple of times in different presentations the Air for Us activity being mentioned. It had earlier names under the Earth Science to Action. It's a joint activity between NASA's Earth Action side of the house as well as the research side where I sit. And we are bringing together the capabilities from NASA, from NOAA, from EPA, and having it in one place for stakeholders to look for. And that is the air quality portal that, as we've showed in his slide, under the name Air for Us or Air for US, air quality information for the United States, specifically targeting our air quality managers and stakeholders. So great work that Kazu and his team are doing with the modeling and the what if scenarios. And so the Tiger team is an excellent opportunity to work with Kazu and his team, with GMAO Carl Mallings and his team, as well as the partners at NOAA and EPA to feed back, like, what is it that you need? What is it that you love that you already have? What is it you don't have? What's your wish list? Let us know, and we'll be working towards what we can within the framework that we have. So we're just really excited to see the progress that Kazu and others are making towards this effort. But I just wanted to is going through some iterations. I just wanted to make sure that that was clear as far as the air for us or air for US. Yeah, that's what I wanted to say.
Thanks.
And then I was just really curious now that I'm up here. Macitis, is that, did I say it right?
Yes.
Okay, great. Is that something that a user has to download onto their computer or to be able to view? And then you mentioned being able to download data, but maybe some data is available. So is it something that folks, like if I'm talking about it, like, oh, there's this great thing that the University of Wisconsin-Madison has where what are the steps that folks have to do? Like there's already, like, can you use OpenDAP, or other APIs to be able to access data, or how does it work?
Yep. So you would go to the Macitis V webpage that I had the QR code on my slide.
Perfect.
You download it as your own user. We have installers for Windows, Mac, and Linux.
Yep.
You run it as your own user. And then for the data, it depends on what you want to work with.
Okay.
So if you wanted to work with real-time goes east, goes west data, radar over the United States, forecast model data, like somewhat near real time, we have a lot of that data available. So the satellite data comes through what we call data servers.
Mm-hmm.
So you can pull in your data that way. For radar data, that comes in through either a data server or threads. Like a thread server catalog.
Mm-hmm.
And that's how the point observation and the grid data work as well. So if you want Tropomi data or OMI or something like that, if you had a thread server where the data lives online, you could load in the data that way and then you don't have to download it locally. Otherwise, you likely need to download the data locally or have it on some kind of a mounted drive.
If you had model data through a thread server, could you look at it that way?
Yep. So if it's on the thread server, you can just, we have several that are in there right now that have like GFS, NAM, the HER, RAP. So you would just choose whatever forecast model run you want, click on the name of the file and click the add source button.
And if we had NASA GEOS model output, GeoCF or GeoSFP or MERA2 in a thread server, you could also pull that in and compare?
It would be dependent on the data format. So as long as it's like, say it's in a gridded format.
Yes.
If it's in NetCDF, HDF, GRIB1, GRIB2, as long as it's written in what's called a CF compliant way,
yes.
then you would just be able to click on it, click add source, and then it would load it in.
Beautiful. Let's talk after.
Okay, so good.
Thank you.
I have a follow-up question online, asking what is a threads server?
Yes. Oh, great question.
Okay, so I forget exactly what it stands for. Thematic something data.
Yeah, it's got too many D's or too many E's. It's like THR, DDF, something like that.
Yeah, so you can access them through like a web browser. You can go to like a .html version, and that'll allow you to click and download the individual NetCDF files, like locally to your machine. Or it's a URL that ends in XML. That XML URL is the one that you can just put into what we call the catalogs chooser in Macitis V. It's all fairly simple to do once you have it up and running. So it's basically the thread server is a remote system computer somewhere that holds all that data that you just access remotely.
Are there other questions online?
While we're on that topic. So as a user, this is so cool, right? So do you have documentation like online of if you're looking for this category of data, here's how you would add it in, or it's already preloaded, like tutorial style to make it user friendly? Or is it like you kind of have to have this background remote sensing?
Repeat the question.
Oh, sure. So the question was, I'm trying to remember exactly how you phrased it.
Do this. I don't even remember what it
Oh, the training documentation. Sorry, my head's going. So she was asking about training for basically how to get and load data into Macitis V. So we have an online user's guide where you can search anything that you want that's in the software. We also have individual tutorials. So if you're interested in geostationary, low Earth orbit, radar, forecast model data, we have individual tutorials that'll walk you through like step by step. So step by step to work with loading in the data, working with it. So there are a bunch of different formulas and derived products that you can create inside of Macitis V as well. So we go through doing all that. You can capture images and animations. We show you how to do all that in the tutorials. We don't have a single tutorial that shows you how to go out and get like a specific type of data, other than I think we have one out there for like gridded new caps data. We were working with NASA Sport on a project to get some of that data loaded in. So I wrote up a specific Machitis V tutorial for that I think is hosted on somewhere on their webpage. But yeah, again, from that QR code, the website, you'll find all the tutorials and documentation.
I'm going to add to this. Machitis V is well established. I mean, people, atmospheric scientists at UVA were using it. I'm going to say 25 years ago. It's well established, so it's only grown. It's well known.
Is it new for the atmospheric composition side?
So Machitis, it could be the oldest software in the world that's still being actively used and supported. It goes back to the 1970s. There's two different versions of Machitis. There's Machitis X. That one's still active and going. If you ever go to the National Weather Service and look at satellite imagery on there, that was made with Machitis X. It's very good at processing really large amounts of data. And then you have Machitis V, which is the newer version. It's still been around 15 plus years. We're built on top of Unidata's IDV, the integrated data viewer, if you've heard of that. That's been around for several years prior to that. So like you said, there's a long history behind it.
Yeah.
PR.
Yeah, get it out there. Get it out there. Yeah.
I've never heard of it.
Oh, sure.
It's
Yeah,
amazing.
yeah, we go to the AMS conference every year. We have the University of Wisconsin booth, and I'm always there demonstrating. So need to get a bigger sign, I guess.
Other questions?
Yeah.
Oh, I'm going back first.
Well, Alex Rutledge, NASA Langley, Earth Science Data Center. It was said that Temple version 4 data are coming out sporadically. This is kind of partially true with respect to backward processing. With forward processing, it's a regular kind of process, data coming every single day. So that should be understood clearly. And why backward processing is sporadic is because the science team has some kind of computational power issues, as far as I understand.
Good.
As the program scientist for Tempo now, I can talk on this one too. Hi, Emma Nolan. So at the Tempo had a prime mission of about 20 months. It's a very short time period in order to meet their primary scientific objectives, which is delivering the science quality data that you wanted for NO2, formaldehyde, ozone, and the ozone profile. The ozone profile broke their computer. And so that is why the ozone profile was not released to begin with. They focused on the total column and the tropospheric column trace gases. And so once they managed to get the provisional data out up to version 3, we focused on the ozone profile, but they reached that during a period of time when they were having their end of prime mission review. And so in order to pass the review, they had to have the ozone profile done 1 month in each of the 4 seasons validated. And so they had to reprocess those individual periods because version 4, which has the profile, started running as continuous, was in September last year, maybe? Yeah, September of 2025. And so that's been running every day just fine. But in order to get the historical periods for the validation, it looks like it's sporadic because they're focusing on that month they need from each of the previous seasons otherwise. So once this is done, you'll see these streams coming through, but it is the ozone profile that takes so long each time, each day. And so it'll take a while to reach version 4. This is something that the team is very much aware of, and we are considering how do we improve this for future versions when they want to reprocess, because it's very painful, I know, from the community to wait for your continuous NO2, your formaldehyde, the things that we're used to seeing very rapidly every day. So apologies, we're definitely working on it. And we're excited by the enthusiasm and the improvements we've already seen with version 4.
And we are glad you're in the room.
We divided and conquered, but I'm very glad I'm in this one too.
Or just stay up here.
No. My lower back aches, so it's hard to sit. So yes, I'm gonna stand.
Yeah, my question is primarily for Dan, but also the other panelist who's working on Tempo. Dan, you've been working on Tropomi and O2 for a very long time. Now that Tempo V4, you will have access to it soon. What are some research questions that really excite you? So what have you been dying to sort of analyze?
Yeah, I think the thing that I'm most excited is looking at hourly emission profiles. So I mean, the first thing that comes to mind is like on-road profiles. We have the rush hours that we are completely missing from Tropomi. So, you know, and also particularly the morning time seems to be highly correlated with the surface. So I'm really excited to look at morning time versus the middle of the day versus the afternoon, specifically for looking at individual sectors of emissions. That's one of many things. Let's see what else. Yeah, looking at individual days. So now, like, if there was a cloud at exactly 1 p.m. and but there might not have been cloud at 2 p.m. So you can just kind of shift your measurement. Some days there was just a cloud just at 1 p.m. and maybe the other 11 hours are fully clear. So, you know, that's really exciting, where days that were completely missing from the Tropomi record are now maybe just a few hours of missing data. So you will have many fewer missing days with fully missing data. I actually put some stats in my last paper on this, which is about like in an East Coast city, it's about 40% coverage you get from Tropomi, but for Tempo, it's probably going to be closer to 70 or almost 80% coverage of days that you would have at least one measurement from Tempo. That's one thing. And then, yeah, just looking at chemistry, different times of day. You know, the lifetime of NO2 is shorter in the middle of the day, but longer in the morning time. So you'll have some, you know, different chemistry, different disparities, different times of day. So that's kind of the short list. But then also intercomparing with GCAS. I'm really excited about GCAS. I know it wasn't your question, but I'm really excited about GCAS and the very high spatial resolution that GCAS has. And so intercomparing Tempo with GCAS and seeing what...
Do you want to tell the community?
Yeah, sorry, what GCAS is. Thank you. GCAS is the airborne measurement on aircraft. It's only flown during certain NASA field campaigns. It has spatial resolution of about 300 meters, depending on the altitude that it's flying. But we usually fly that instrument over cities. So this summer we're going to fly it over Houston, maybe Dallas, maybe the Permian Basin. But in the prior studies, it's been flown over New York City, over Chicago, also over Houston, other cities randomly. I think they were just out in Japan as well. So it was really high resolution. We can actually get individual plumes, see individual highways that the satellite data cannot see on its own, but then linking that with the satellite data with Tempo specifically could be really, really exciting. That's the short answer.
Any other question? Pat?
Is HAQAST easier to use than IDV?
In my opinion, it is. So we don't compete with IDV at all. I don't want to make it sound that way. We collaborate with each other and we have monthly calls. When they check something into their code, we get it and vice versa. So I like the way that HAQAST V is set up better as far as the, especially the main display window. It's easier to work with like a single window with like multiple tabs and panels and stuff like that. But one of the biggest differences between HAQAST V and the IDV is the amount of data that you can work with. So like I had mentioned earlier, data servers for satellite data. So if you just have level 1B, ABI, CONUS data, if you load it in as a gridded data source, which is all that you can do in the IDV, you only have reflectance and the data quality flag field. In the HAQAST V, you can set up a local server. It doesn't take much work to do, and there's documentation on how to do it. But then you get all the calibrated values like temperature and albedo and things like that. We also have our JPSS chooser, so that's how you would work with like VIIRS, CRIS, ATMS data. Just a couple brief differences between HAQAST V and the IDV, but overall the functionality is the same. So if you know how to use the IDV, you would know how to use Makaitis V. And people pick up on it really quickly too. Like we have a high school workshop that comes through once a year. And we have a Makaitis V session where we break the students up into small groups of 3 or 4. We pair them up with the scientists from our building and they'll do a case study in Makaitis V. And within like a few minutes, they're clicking through, they're already making their own enhancements and displaying data and they're doing a lot with it. So it's very intuitive, I would say.
Other questions? Okay.
A question to Amber. When you showed those fire place detection images, let's say smaller area covered versus big area covered from a new sensor. When you're kind of calling for continuity, what do you suggest to do? Reduce the area in the new image or enlarge area in the old image? Because that's what continuity means. They should stitch together, right?
I'm not sure I understand the question, but so I'll come back at this with the one customer who's very interested, and that would be the EPA. So they hold our nation's national emissions inventory, and they use and the fire emissions inventory, and that goes into the NEI, and they use HMS data. So what HMS data is a NOAA product, and it puts together. It used to use FIMMA, AVHR, but they don't use that anymore. But if you go back, it does. VEERS, MODIS, GOES. And so if you have, and sometimes if they see a fire and there's no detection, but there's a plume and they know it's a fire, not a stack, they'll add it. So it's a human satellite product. And at this place, at this pixel, they'll only take one. So if all of the instruments say there's a fire here, it's a fire here. So they don't double count it. But that's what the EPA uses as the basis, or one item they use. They also use Forest Service data. They work with states, so they integrate what the states are saying. So, but for farmland, you really don't have agricultural lands. You don't have that kind of data. So they would use fire detection data, and they would use an algorithm to say how large the field size is that burns. So on average, they know, working with the states, they're in most cases underestimating. And so they try to get better all the time. So it's getting the right ground-based estimate for the entire, United States. And also they get parts of Mexico and Canada too, as background.
Yeah, I asked this question because it looks like there is a direct conflict between continuity and accuracy. And actually, a few years ago, I worked with some NASA project. At the science team meeting, the PI explicitly said we should value continuity more than our data accuracy, and the project produced and still is producing long-term climate data records. So in long-term climate data records, you don't want to see your thermal flux kind of having break like this.
That's right.
So it's important to stitch them together, and so we have to sacrifice accuracy of our retrievals in certain sense.
Okay, yeah, all right, so different projects, yeah.
Yes.
I don't know if you're talking about Louis Giglio or Vaughn, or like what school of thought. So and AVHR doesn't reprocess, so it's hard to connect to the MODIS era, and yes, there is a climatology, but for fires, it's not very accurate depending on where you are. And they would want, it depends on your customer. But if you're talking to the fire community and asking questions like, okay, is this climate change thing really having an effect on the Arctic and boreal in terms of fire increases? You want accuracy. You want accuracy. And you're not going to have fire radiated power back to 1972, but you could get AVHR and Landsat data. Really hard to process, but you could. And the Arctic and the boreal, as you know, is warming the fastest and the fire is increasing. So you've got fire regimes that are going from a mean of 3,000 years in the Arctic to less than that. So it's questions we need to answer because these are feeding back to systems in terms of hydrologic systems, snow and ice melting, permafrost, thawing. So it's these are big questions. So in that you want the accuracy. And the climate, the CCI is, I think, what you're talking about. That is not accurate for areas that don't have motives to correct it, for times that don't have motives to correct the data. So for Siberia, they don't have a good data record, but for Alaska and Canada, they have a good 50-year record. So there are ways to correct it, but only if you have data. And all that remains of, and you probably know this, of the AVHR is GAC data. So that's 4 pixels, 1 kilometer, about 1.1. You skip 1, you skip 2 lines, and you get the mean of the 4. So it's only for large fires that will work, but they're large fires in the boreal. So it works, but it's challenging. And Lewis is working on that globally now.
So I think we're not, unless Emily, you have a quick question?
Okay. I have one quick comment. If we're talking about Air for Us, it's Carl Mollings that is the lead of that Tiger team. So if you want to join that one, any of the stakeholders, please write to Carl.
Yes.
Well, let's thank all our speakers.